So next is Malik Bossett, and he is another NAC-8 student from the Northern Arizona University, whereas he's a sophomore. And for his project, he worked with Ralph Catula at the University of Wisconsin-Madison, and he's going to share with us today his work on analyzing the surface brightness of galaxies in the Perseus cluster. So go ahead and take it away.
Hello everyone, my name is Malik Bossett. As you heard, I'm a sophomore. I go to Northern Arizona University. And my mentor is Ralph Catula from UW-Madison. And I just want to thank everybody for coming to my talk today. So before we get into the project itself, I want to talk about a little bit of background. So you want to know the difference between field and cluster galaxies. So field galaxies are more of like galaxies that are outside clusters, so kind of like the loners of the universe. So for example, NGC 2683 is kind of like outside of any certain cluster. But then you have cluster galaxies, of course, that are galaxies that are part of the cluster. And as you know, galaxy clusters are rich environments with many galaxies clumped together in the largest gravitationally bound objects in the universe. They also stand out from their surroundings by having a noticeably different mix of galaxy types. So earlier research that I will talk about a little bit later on has shown that lenticular galaxies, so galaxies that are kind of like in between the spiral and elliptical galaxy, in the field, which are outside clusters, show a variety of intrinsic light profiles. So from ranging from exponential profiles where there's just a gradual dip in brightness going from the center of the galaxy out towards the outskirts, to puffed up profiles where there's actually excess light in the galaxy outskirts. And then you have truncated profiles where there's basically a big drop in brightness going from the center of the galaxy to its outskirts. So we'll first also learn definition of surface brightness. So surface brightness quantifies the apparent brightness or flux density per unit angular area of a spatially extended object, such as a galaxy or a nebula, and they're usually measured in magnitudes per square arc second. As you see in this picture here, this is an example of a galaxy which has a relatively low surface brightness. So this particular galaxy surface brightness at the center is actually dimmer than some galaxies with high surface brightnesses at their outskirts. So in the overview of this project, so me and Ralph, we studied the surface brightness profiles of a large number of galaxies in the Perseus galaxy cluster using very deep imaging data using the Subaru HyperSuprimeCam instrument. And basically this project is we're trying to see whether the lack of diversity in the Virgo supercluster is a more general phenomenon, or it's just a Virgo-specific peculiarity. And the second one I'm about to talk about next. So as you see here from an earlier paper written by these three astronomers, you can see that there's three different types of surface brightness profiles. So you can see on the left here, that's the exponential, where it's just a gradual decrease of brightness. Then the type 2, you have the puffed up profile, where you have just a little bit of an increase in brightness going out towards the outskirts of the galaxy. Then you have the truncated profile, where there is kind of like less of a break, but more of like a deep drop in brightness. So in this study, field lenticular galaxies, so lenticular galaxies outside the cluster, were equally divided between the three main types of lenticular galaxies based on surface brightness. However, in the Virgo supercluster, there are mostly galaxies they're mostly made up of type 1 profiles. So mostly galaxies where there's just a gradual decrease of surface brightness going out to their outskirts. And these scientists wanted to find out what's the reasoning behind it. And that's basically what me and Ralph were trying to figure out. So basically kind of like continuing these scientists' research. So first what we did was we downloaded optical images from the Subaru telescope and uploaded them to the image processing program DS9, so DC image processing system made by Smithsonian. So that allows you to edit different pictures. So that allowed us to edit pictures of the Perseus cluster of galaxies. And next, we built catalogs of the prominent galaxies in the cluster from different images. So from this catalog, we're able to basically change the number of galaxies that the that the program can detect and allow us to map out. Then we use Python in order to create ellipse profiles that show the different regions of galaxies in the cluster. So this is particularly important too because we want to know whether the center of the galaxy is brighter than the outskirts, or if there's like a little bit of an increase in brightness of the galaxy in the outskirts. So as you can see here, in particular, in particular, the galaxy on the upper left, so it has like a bit of green in the center. So that's where the program identified the center of the galaxy. Then the blue pretty much is showing the outskirts of the galaxy. So that would allow the program to specifically show, okay, these are the different regions of the galaxy, and that allow it to identify whether the center is brighter or whether the outskirts are brighter. And then next, we had to create the plots that compared the radius of the ellipse radius and the brightness of different parts of the galaxies using a program called TopCat, where basically kind of files that I created were .csv files, and then created them into plots. For example, this plot. So this actually shows a plot of different galaxies that me and Ralph analyzed. So first we have the intensity, which is on the y-axis. So that's how much light per unit area. Then we have the SMA, which is at the x-axis. So that's basically the semi-major axis. So kind of like showing the radius of the longest ellipse and then just going all the way down to the center. So as you can see here, the general pattern is that the surface brightness intensity is shown to decrease as the radius increases as we get to the outskirts of the galaxy. However, there are a few galaxies where the brightness kind of goes up a little bit near the outskirts. So that could be the result of, oh, maybe there's a supernova in that part of the galaxy, or there could have been excess star formation happening in that part of the galaxy. And that's basically what we saw with these more detailed, kind of like easier to understand surface brightness graphs. So on the left, on the right here, you can actually see two galaxies that have the kind of like the exponential profile. So basically, like the light just the surface brightness drops off a lot when going from the center to the outskirts. But then on the left here, you can see two other galaxies that actually kind of have the puffed up profiles, kind of like the ones where there's a little bit of an increase in the surface brightness on the outskirts. So that was actually interesting find, because then that way we are able to determine if this phenomena is specific to the Virgo cluster, or if it's a general pattern, between cluster and field galaxies. So some of the future work that we plan on doing is we plan on comparing the brightness plots with the three different types of surface brightness plots created from the Virgo study, to again determine whether the peculiarities are specific to Virgo or is a more general pattern. And we're also going to try to calculate the surface brightness of each galaxy using this equation right here. So you have S equals the mass of the galaxy plus 2.5 times log base 10 of the area of the galaxy. So what is the importance of, what is the takeaway from this project? So really the takeaway of this project is ultimately this research will help astronomers better understand the evolution of galaxies, galactic clusters, and of our own galaxy, the Milky Way. And thank you.
All right, great talk, Malik. Thank you so much. And do we have any questions? All right, Svea, I think, has a question.
Yes, hi. Great talk, Malik. This is very exciting work. Congratulations. A quick question. So you mentioned the three different profiles, or the three different types of profiles. And profile, I'll give you a couple seconds to get to that slide, maybe towards the beginning. So the type 2 and type 3 profiles, so that one, perfect. So the middle and the right plot. So you point there that you see a break, and in the middle one, the luminosity starts going down, and the right plot, or type 3, then the luminosity maybe goes up a little bit. And I think throughout your talk, you mentioned that you maybe observed this in the galaxies that you study, that uptick. So was this, did I understand correctly that this uptick is something maybe like supernovae that are increasing the luminosity on the edges of the galaxy? And what would be the cause for the decrease? So for type 3 profile.
So we aren't exactly sure of the cause of the little bit of uptick in brightness in the outskirts of the galaxy. Our kind of like best deduction is either there's a supernova that occurred in the outskirts of that galaxy, or if there was excess star formation coming from a potential galactic collision. Honestly, I guess for the type 3 profile, since it would be more, I guess like from there it would be more of like it's more of a gradual decrease in brightness. So like it's kind of like it's like there's a drop off like the exponential one. So like there might be little tiny upticks compared to the type 2 where there's like probably a big uptick. So that's really what type 3s are. There's more of like the brightness overall is going down, but there's like tiny upticks.
Okay, sounds good. Thank you so much. Great work.
Thank you.
Okay, and we have another question from Andrew Baker, and he asks, are you analyzing only S0 galaxies in the Perseus cluster or all types of galaxies?
So primarily, this previous paper that we built off on was mostly studying lenticular galaxies. We also potentially plan on also studying elliptical and spiral galaxies in the future. So that's that question.
Let's thank all of our speakers again. This was a great set of talks, and thank you all for coming tonight.